Ladies and gentlemen, class recording has started. So, on Wednesday and Thursday of last week, we started on the last section of Chapter 9 that dealt with, hold on a second, there we go, that dealt with planetary motion and orbits. And we said that as part of this unit, we actually bring two parts of the previous things that we discussed in this chapter together. And Newton basically did that with this equation where he took the concept of gravitation, took the concept of centripetal force, put them together to calculate the speed that the moon travels around the Earth. And we can apply that to any circular orbit, that as long as something is going in a circular path where gravity is providing the centripetal force, this is how fast it has to go. That mass, right, is only the mass of the object that is being orbited. So in the case, if we're calculating the speed that the moon travels around the Earth, this mass right here would be the mass of the Earth, because that's the mass that determines the speed of the satellite and how fast it goes around the Earth. The d is the distance that object is from the center, just like we've talked about up until this point. But that is a very specific speed, and it only applies to a circular motion. What happens if we're not at that exact speed? So first, what if we're slower than that speed? What's going to happen? You hit the Earth eventually, right? Might not be right away, but eventually you'll hit the Earth. But if we go faster than that speed, we move off of that perfect circular path into an oval path. That was terrible underlining, but all right. That we call an ellipse. What? No, I was actually trying to underline it. So here. Let's call it a stretchy circle. No. I mean, oval, right? You know, so yeah, right. Good. Hold on. The speed has to be just right to orbit in what shape? In a circle. That's what the speed has to be just right. To orbit in a complete, perfect circle. Right. Can't go slower than that speed. Because if you go slower than that speed, like I said, eventually you're going to hit the ground. Might not be right away, but eventually you'll hit the ground. Okay? Actually, there's now actual minimum height, because in this formula, technically we could put any distance in there that we wanted to. We could get an object to orbit at this height right here. Now, if we move fast enough, and if it didn't have things like trees and mountains and stuff in the way, you know. But, you know, the distance off the surface only affects how fast it would have to go to orbit, but not if it can or can't orbit. Now, as we see here, and we'll get to this in a little bit, the farther away you go from the object, right, if d keeps getting bigger and bigger and bigger, how does that affect the speed that you have to travel to orbit? Because where's d at in that equation? So if d gets bigger, v gets smaller. So the farther away you are from something, the slower you actually travel in order to complete that circle. But again, this only applies to a perfect circle. So what if it isn't, you know, what if we're not at that speed? Slower, we hit the ground. Faster, we move off of that circular path into an elliptical orbit. Okay? Now, we knew that objects traveled in elliptical orbits before we knew why. Did I tell you the story about Brahe and Kepler on Thursday? Okay. Tycho Brahe. He's Brahe. So, no. So there you go. So, wow. Now you know. Did you know that before? Okay. That's terrible, actually, that you probably knew that. But you might be less than 1% of the people that watched that movie that were like, I understand that joke. So anyway, guy on the left, Tycho Brahe. I believe, if I remember correctly, he is Danish, and not a Danish, but from Denmark. Okay, so yeah. No, I think that that's actually his mustache. Like, I think like his mustache
So
actually comes out like this. So, yeah, he's Walrus C. So, Tico Walrus Brohe. So, anyway. All right, so this is terrible. Like, why don't we just, like, we'll give him, like, some money, like, yeah, they're not pronounced enough, all right? So we were like, what?
Well, now you gotta put it harder on the other.
Who? Oh, Taft. I was like, who? That's kind of, I mean, that's kind of obscure too. That we're like, this guy looks like an obscure president from the United States. Like that's just. This class is full of obscure references.
We have to put harder on Kepler now, so it's like a yearbook.
So we have to like what?
Like put harder on.
Oh, like this.
Totally looks like a fifth grade yearbook now.
Totally does. There.
So
How's that? So, good thing this one's getting recorded. So. All right. So, Brahe, in the 1400s, makes a long series of very precise measurements regarding the position of stars, the planets, the sun, the moon, where all of these things are over a long period of time, years and years and years. Kepler takes Brahe's measurements and starts finding patterns within them. Now, like it says here, he didn't know why these patterns existed. All he knew was that they did. Looking at the data, he realizes that these patterns exist, but why? He had no idea. It wasn't until Newton introduced the idea of gravity and the effects, the things that influence the amount of gravity, do we start to all piece it together and go, oh, that's why these things happen. Okay? So, 3 laws. First, planets follow elliptical orbits with the sun at one focus of the ellipse. First, did we do this the other day or no? Okay, we didn't get this far? Fine. Yeah, all right. So, yeah, it was kind of a crazy couple days. So, Yeah. Hannah got this far, but that's about it. So, all right. Michelle, I don't think, did we get this? Okay, you got this far, but you didn't get all the way to the end. So, all right. This is an ellipse, okay? An ellipse is an oval, basically, for lack of a better description. But to make an ellipse, this is what you would do. This is not how it's mathematically defined, but practically speaking, this is how you make an ellipse. So you put, say, like 2 push pins right here in a piece of cardboard or whatever it may be, okay? Those 2 points we refer to as the focus points, or the foci. Next, you take a string and tie it in a loop. One of them goes around the one push pin, it goes around the other push pin, and then if you take a pencil and stretch it out, you get like this triangle shape, okay? If you continue pulling the pencil as tight as it can go while moving it around that path, what you'll end up with is a series of triangles where it always goes around the 2 push pins and out to the edge of the circle. So it looks like that, okay? Good with the idea, at least to begin with, okay? Now, the mathematical definition of an ellipse is that the 2 sides of the triangle are always, the sum of the 2 sides of the triangle is the same throughout the entire ellipse. So, we back this up here, okay? If we take this side plus this side, we would get a certain answer, okay? And then, as we moved the pencil around, and we created this new triangle, this side and this side added together, the sum of those 2 sides, would be the same as the sum of the pink triangle's two sides, which you can kind of see because it's just kind of like flipped a little bit. It's a little bit harder to see when we go something like this. Okay? This side and this side, the sum of those two is the same as the other two sides. So the sum of the distance between the two focus points always remains the same. One gets shorter, one gets longer, but it's always the same. Okay? Depending on how stretched out the focus points are, will determine whether it's more elliptical or more oval shaped, or if you bring them closer together, it's less oval and more round. If the two focus points are actually right at the same spot, we get a circle. So circles are ellipses, but not all ellipses are circles. Okay? A circle is a say again? About ellipses or about squares and rectangles?
Just think of it the same way.
Okay.
Squares and rectangles.
Right, yeah, right, yeah. Like all squares are rectangles, but not all rectangles are squares. All circles are ellipses, but not all ellipses are circles. Right? Mathematically, the equations are much more complicated. You know, that's
You could use
so.
a little like do that before. You know, rectangles are squares.
Yeah, you know. But so we got that. But more important, maybe not more important, but one of the focus points of that ellipse is always the sun. There's nothing at the other focus point in reality, you know, or in, you know, as far as orbits are concerned. You know, to make an ellipse, you would put the two push pins, but in reality, like out there in the world, there's nothing at the other focus point of the ellipse that is the orbit of Earth. The sun is at one, but there's nothing at the other one. But from a more big picture standpoint, another piece of evidence to suggest that the Earth is not the center of the universe, right? That things don't revolve around the Earth. The Earth actually goes around something else, in this case the sun, and now we know that the sun isn't the center really of anything either. It's just some kind of random point out there that we just go around, but you know. Okay? Do you have a question or are you good?
So with the orbit of the planets, sets out as
No, because, and we'll see why in just a second here, that once it gets into this elliptical pattern, unless there is another force that acts on it, nothing will change it. It will stay in that pattern, okay? Without external forces. Okay? Right, go ahead. Yeah. Just flips the shape. It just flips the shape of the ellipse, right? Yeah. I mean, there's no difference between this ellipse and like this ellipse. You know, yeah, it's just where the focus points are. But the definition of an ellipse is still the same. It would still be the distance from the two focus points. The sum of the distance between the two focus points is the same. Okay.
So why are certain like those colors like along the
Right.
we have like certain
Right. Again, that gets back to this. How much faster than the speed to create a perfect circle are you going? If you're just a little bit above the speed to create a perfect circle, your orbit is not very elliptical. But if you're much greater than the speed to create that perfect circle, now, right, you get this more elliptical shape. This is something that's only going a little bit faster than the perfect circle speed. This is something that's going a lot faster than the perfect circle speed.
so it's velocity.
Yeah, velocity to determine, because remember, an orbit doesn't happen without the horizontal motion, right? Gravity's still acting on it, but without the horizontal part, it doesn't happen. Orbits don't happen.
Our Earth is like moving.
Right. Just like the moon, just like we talked about the moon the other day.
It's moving forward.
That when it became into existence, right? We're still dealing with the fallout from the Big Bang, right? Everything is kind of moving to begin with. Then gravity starts pulling small things together, and then those small things start pulling other small things together, and they start making bigger things, and bigger things. Yeah, basically, yep. Well, that gets a little bit more complex. Not that I want to finish this up today though. So, but yeah, I mean the orbit part is because we're still dealing with that movement of there are very few things in the universe that are sitting still, right? Now, granted, relative speaking and stuff like that, but absolutely speaking, there's very few things that are sitting still. Everything's basically moving because it was at one time moving, like Big Bang kind of stuff. Yeah. All right. Kepler's second law. First, let's read. As a planet moves in its orbit, it sweeps out an equal amount of area in an equal amount of time. Not that kind of sweep, no. Yep. All right, so first, we need to deal with an equal amount of time. So the picture on the left shows you 1 month. Let's say that this one down here in the bottom part, let's say this is like January 15th, and this is like February 15th. So 31 days. Okay? And then this is August 1st, and that is September 1st. 31 days, right? Equal amount of time. First, if we look at this distance, how far that object moves in that month versus this distance, right? Which one did it move farther? Left or right? Along the orbit. Unless you guys can see, right? This distance appears to be longer than that distance does. Yes? So, if we talk about the distance that it moves in 1 month, if it moves a farther distance this month than it did this month, what does that suggest about its speed? It speeds up here, and it slows down here, right? Just because the path is elliptical, well, one of the other consequences of the elliptical path, right? We said that if it's a circle, something doesn't speed up or slow down, it just changes direction. But when we move off of that circular path into the elliptical path, now we actually see some changes in the speed of an object. Okay? Mathematically, and I wouldn't have you do this in any way, shape, or form, but this gray area right here, it is a gray area. It's kind of triangle shaped. Not exactly a triangle, right? I'm just going to move on after that. This gray area and that gray area, although not a gray area, a scientifically proven fact, the area, I know we've used how about this gray section and that gray section? Now that's just what you hear, right? Mathematically, those two shapes have exactly the same area. Okay? They're not triangles because the one side is curved, but this quote-unquote triangle is kind of shorter and wider, but this triangle, the blue one circled in blue, is more of taller and skinnier. But area-wise, they are exactly the same. Same is true over here and over here. Those two gray sections have exactly the same area, as long as we're dealing with an equal amount of time. So, while this is Kepler's second law, a planet moves in its orbit, it sweeps out an equal amount of area in an equal amount of time, the application of that, or the reason behind it, is because when planets move around the sun, they do not travel at a constant speed. The farther away they are from the sun, the slower they go. The closer they are to the sun, the faster they go. All right? And if you think about it, because of gravity. As things are moving away from the sun, gravity is pulling them back towards the sun. That causes them to slow down. When they get out to this spot right here, that's the slowest they're ever going to go. But then gravity turns them back around and starts bringing them back in. Ready? It's exactly the same application, right? Yes. Yeah, so but it's working on it in which way? If it's getting away from, it's making it do what? Speed up or slow down. If it's getting farther away from the planet, or sorry, if it's getting farther away from the sun, but gravity's still pulling it back in the opposite direction. If something's moving to the right, but you're pulling on it left, what's going to happen to it? Does that make sense if Luke tells you to do that, right? If this picture, yep, because gravity's making it lose speed, just like when I do this, right here, right? Gravity's making it lose speed because as the farther it gets away, gravity's still pulling it in that downward direction, right? And then once it turns it back around, when it's coming back to the sun, it's going faster and faster and faster and faster, because just like on the way back down here, right? Right? Yes, Fred.
If you have something that goes really fast,
No, okay.
you have the speed of where you're going.
Yeah.
You have something that goes like that faster.
The speed of light is a different story, okay, because that's something different, right? But like when we're talking about looking at this, I'm going to erase this so Krista can see what I'm doing, right? When we're talking about this object, okay, and watching it go around the sun, right? It's slow out here, but then fast through here, and then slow out here, fast through here, slow out here, fast through here, slow out there. Does that make sense? It's kind of like slingshots as it goes around when it's very close to the sun. At this point right here, that's the fastest it's ever going to go, because that's the closest it ever is to the sun. Does that make sense? The speed keeps changing, which we actually use to our advantage sometimes, because when we're trying to send something like to a deep space or whatever it might be, right? If we talk about slingshotting something around a planet or whatever, we talk about Voyager 1. We talked about Voyager 1 and what? Yeah, we've talked. I think we've talked about Voyager 1, but they basically did that with that satellite. The intent was to send the satellite into deep space out of the solar system. It would get there eventually because of inertia. It just keeps going. But the faster we make it go, the faster it gets there. So what they did, the original mission of the satellite was to go to Jupiter and take pictures. Yep. That they got it in an orbit around Jupiter and went faster and faster and faster and faster and faster until it got here, and then they basically turned the engine on again. And so now it gets shot in this direction, okay? But it's going faster now than it was before, because that engine was accelerating it from an already greater initial velocity, just because gravity pulled it in and made it go faster and faster and faster. So, yeah, as long as we get it in that orbit, we can tell how fast, when it's closest, when it reaches its top speed, and then we let it go. So, yeah. But that, the gist of this, Kepler's second law, is that the speed of planets is not constant as it's going in its orbit. It speeds up and it slows down. No. Well, it is. So here. Remember, this has to be all one equal interval of time. So here, this is 1 month, but that's 1 month as well. So if you look at the distance along the orbit that it travels much farther along its orbit in this month than it does in this month. Okay? But the area of those two gray shaded sections is the same. Okay? All right, good there? All right, last Kepler's law, okay? So, here's what it says. The period t of a planet increases as its distance from the sun, r, raised to the 3/2 power. That is, t is equal to the constant r to the 3/2 power. Okay? If you read that, you'd look at that and go, yep, sure it does. Okay? All right, so let's talk about what it actually means. Here's the analogy that we'll use. Okay? So, if you and Usain Bolt have a 100-meter dash race, okay? Yeah, so after Luke wins, right? Okay. So let's say Usain Bolt runs twice as fast as you, okay? Okay. Either way, whatever, you know. Let's just say, hypothetically, right? One runs twice as fast as the other one. So let's say, just hypothetically, let's say Usain Bolt runs his 100-meter dash in 10 seconds. Okay? I'm just saying, if he runs the 10-second race, right? If he runs the 10-second race and he runs twice as fast as you, how long is it going to take you to finish the race? 20 seconds, right? That's, you know, he runs twice as fast, right? And that's because you both go 100 meters. All right? But let's say not only does Usain Bolt run twice as fast as you, but his race is 100 meters and your race is 150 meters. Okay? So now he's done in 10 seconds, but now it takes you what? 20 plus half of 20, right? Because it's right 150, right? So it would take you 30 seconds to complete your race, right? Does that make sense? Okay? Because you ran 120, so you're going to run 150 and 30, okay? So, two factors working there. Yes, you are slower than Usain Bolt, but you also have to run a longer race, okay? What this says is basically the same thing. It says that as we get farther and farther and farther from the sun, it takes planets a longer time to complete one orbit, which I think most of you would probably go, yeah, right? It's a bigger orbit, okay? But the thing is, it's not a nice linear increase. That if one orbit is twice as big as another orbit, it won't take that planet twice as long. Because not only are the orbits bigger, but the planets also travel more slowly. So Jupiter has a much bigger orbit than us, but it also travels more slowly within that orbit, so it takes longer, but not at a nice linear increase over what our orbit is. Okay? So not only are the orbits bigger, planets also travel slower. The other point, and we've kind of already discussed this point when we talked about circles, is that the period of an orbiting planet or moon depends on the mass being orbited. It does not depend on the mass of the planet or the moon itself. So we talked about if we put the space station in orbit, it has to travel the same speed as people inside of the space station do in order to orbit, because it depends on what we're orbiting, the Earth. If we took Jupiter and put it in our orbit, and we went out to Jupiter's orbit, it would take Jupiter 365 days to make one revolution around the sun, because it doesn't depend on the mass of the thing that is orbiting. It depends on the thing that you are orbiting and the distance, right? So we could put any planet in our orbit, and it would take exactly the same amount of time to complete one orbit. Okay? Good there. Okay. I mean, at least understand it for now. Okay. Questions-wise on the test, we're talking purely conceptual. Right? No calculations or anything like that. Okay. At least not from this. All right. For those of you that weren't here on Friday, I don't know if you noticed or not, but I did put up a review assignment that contains problems from this chapter, the end of the chapter. Right. And here it is, if you want to look at it this evening, right? Or even if you were here on Friday and you didn't write it down. There it is. Answers are down at the bottom, so if you want to consult those, go from there. Okay? Yeah. Well, it's available, but I didn't make it available to you. Do you really want it? I mean, if you really want it, I can get it for you. But I made it available. Oh, sorry. I should probably stop the recording, but so in case Krista wants to know about this, I made it available to everybody last year, and like 3 people out of like 4 classes worth of people signed up for, like, to get it. So But anyway, yeah, if you really want an electronic version of it, I can get it for you. All right, so test tomorrow. Note card, right? All that good stuff, things like that. It's like actual real test. We have calculator, definitely. As far as making your note card, I will give you masses, like if you need to know the mass of the moon or the mass of the earth or something like that to calculate the gravitational, I will give that stuff to you. You don't need to memorize those things. I'll give you the universal gravitational constant that we talked about in the first part of this unit. So all that stuff will be there for you. Okay? The formulas you should write down, though, but the constants I will give. Nice. All right.